So next I want to talk about the binomial theorem. And the binomial theorem tells us how we're going to expand binomial terms like x plus y to the fifth or x plus y squared or something like that. The way that you're taught to do this in school, high school or wherever, is you can have Pascal's triangle. And then Pascal's triangle gives you the coefficients for the term that you're going to have. Okay, so for example, if you wanted to have x plus y to the fourth, what you can do is you can compute, you have x to the fourth, you'll have an x cubed y, x squared, xy cubed, and y to the fourth term. So all the variables there are to the fourth power. So meaning that you have, these are fourth degree polynomials in two variables is what I'm trying to avoid saying. But here you have x to the fourth, y to the zero, x cubed times y to the first, x squared, y squared, x to the first times y cubed. So all the degrees there add up to 4. So the degree of a polynomial in more than one variable is you have a third degree polynomial for x, a 1 degree polynomial for y, and then you add the degrees so that they're all fourth degree. But the main thing here is you look at, since this is to the fourth power, you look at this row of Pascal's triangle. So this has a name called Pascal's triangle. And those tell you the coefficients that you're going to use for each of the different powers. So you're going to have 1x to the fourth plus 4x cubed y plus 6xy squared, x squared, y squared, plus 4xy cubed plus 1y to the fourth. And again, you take those values for your coefficients. This is the binomial theorem. The main connection that the binomial theorem makes that's not obvious, at least not until right now, is that the coefficients that you're going to have for each of the terms are nothing more than binomial coefficients. Okay, and this is why they're called binomial coefficients. So for example, we saw previously that this is this row 1 3 3 1 is 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Okay, so that's that pattern there. And if we were to do this with 4, say I were to look at 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. 4 choose 0 is 1 because you have 4 things you want to choose 0. There's only one way to do that. 4 choose 1 is 4. And you can either think about the formula or you can just think about intuitively, what is that counting? That's saying if you have 4 people and you want to make a one-person team, how many ways to do that? Well, 4. You can have any one of those 4 people make your team. So that's one way to do that. 4 choose 2, we need to use the formula. So this is 4 factorial over 2 factorial times 4 minus 2 factorial. So that's 24 over 2 times 2, or 24 over 4, or 6. And then 4 choose 3 is the same as 4 choose 1 by symmetry. That's also 4. And likewise, 4 choose 4 is the same as 4 choose 0 by symmetry. That's 1. So you really do get the numbers 1, 4, 6, 4, 1. Okay, so that gives you that row of Pascal's triangle. So the binomial theorem tells us that when you raise x plus y to the nth power, the coefficients that you're going to get are going to be those binomial coefficients n choose k. Okay, so that's the binomial theorem in a nutshell. So for example, if you were to have, I've already done a few examples here, but if you were to have x plus y, say, to the fifth, you would have an x to the fifth, x to the fourth y, x cubed y squared, x squared y cubed, xy to the fourth, and x to the fifth terms. The coefficients in the beginning and the last would be 1. Then you'd have 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Okay, so this would end up being x plus y to the fifth. Again, you could think about this. You can still use Pascal's triangle, but you get 1, 5, 10, 10, 5, 1. Okay, so that's the binomial theorem. The binomial theorem is used in lots of applications, so I want to talk about just a few of these. For example, it turns out that if you add up all the binomial coefficients, say, let's work with 5. So if you have 5 choose 0, plus 5 choose 1, plus 5 choose 2, all the way up to 5 choose 5, if you add all of these up, this corresponds to adding the rows of Pascal's triangle. So maybe I better hop back up here. But if you were to add up the values across each row in Pascal's triangle, you would end up, in this case, you would end up with 32. And in the case above, if you have 1 plus 4 plus 6 plus 4 plus 1, you'd end up with 16. 1, 3, 3, and 1 add up to 8. 1, 2, and 1 add up to 4. And then 2 and 1. So when you add up all these values, it turns out that what you're doing is you're adding, and you get a power of 2. So here you get 2 to the 0, 2 to the first, 2 squared, and so on. So this 32 is 2 to the fifth, and the reason why it's the fifth is because this is the coefficients that you use when you have x plus y to the fifth. At least that's the way I think about it. So those are associated together. So if you wanted to add up, say, the 7th row of Pascal's triangle, when I say 7th row, just to be clear, I think of this 1, 5, 10, 10, 5, 1 as the 5th row, because I think of the top row as the 0th row. So this is the 0th row, 1st row, 2nd row, 3rd row, 4th row, 5th row. Okay, so that's the way that I think is the most natural to count, so that your 5th row is the 1, 5, 10, 10, 5, 1. So if you think about what's going on here, it turns out that this really just amounts to knowing that 1 plus 1 is 2. So if you look at 2 to the n, this is really just 1 plus 1 to the n, and then you can use the binomial theorem. And the binomial theorem says that what you're going to do is you're going to have the sum from k equals 0 to n of n choose k times 1 to the k times 1, so our x is 1, and our y is 1, so times 1 to the n minus k. And this is really nothing more than the sum of the binomial coefficients. Okay, so that's the sum of the values n choose k. So when you add all of those up, you end up with 2 to the n. Okay, so that's the binomial theorem, and the binomial theorem makes that really easy. One other thing that you can notice is that if you were to add up the alternating sums of the binomial coefficients, so if you were to make every other term negative, okay, if you were to add those up, what you would end up getting is 0. And I'll let you figure out why that is. But if you were to add those up, you end up with, except for the first one, I guess, because that's the 0th row. But if you were to start at the first row, you'd end up with 1 minus 1, 0. 1 minus 2 plus 1. 1 minus 3 plus 3 minus 1. 1 minus 4 is negative 3 plus 6 is 3 minus 4 is negative 1 plus 1 is 0, and so on. So all of these rows have to add up to 0. Okay, and so my hint for figuring out why that's the case is just to realize that 0 is 1 minus 1. Okay, so I'll let you fill in the details there. Other fun facts with Pascal's triangle that I think are worthy of exploring very quickly, just because binomial coefficients are cool, is that it turns out when you add, you have to think about this in the right way, but it turns out that when you add the diagonals of Pascal's triangle, you end up with 1, 1, 2, 3, 5, 8. Hopefully you realize where this is going. 13. What you're getting, so you have 1, 1, 2, 3. Oops, I still have it on my line setting here. 1, 1, 2, 3, 5, 8, 13. But it turns out what you're getting are Fibonacci numbers, which I think is a pretty cool way for Fibonacci numbers to appear out of Pascal's triangle. So even though you've probably seen Pascal's triangle a bunch of times, not many people know that when you add up the diagonals, you actually end up with the Fibonacci numbers. Okay, so this is the binomial theorem. The last thing I want to say about the binomial theorem, and one place where it's useful, is in calculus. So for example, in calculus, if you are trying to compute, say, the derivative of x to the n, where here n is a positive integer, you know what that should be. But just by definition, if you're using the limit definition of the derivative, you end up with the limit as h goes to 0. I have an h and an n, so I'll try and write that very carefully. this is going to be x plus h to the n minus x to the n over h. And so this binomial coefficient here tells you that what's going to happen is you're going to have x to the n plus n choose 1 times x to the n minus 1 times h plus n choose 2 x to the n minus 2 times h squared. So this, I'm just going to call this h squared times g of x minus x to the n. So this g of x term here, by the way, is actually a function of two variables. Let me call it g of x and h. It's really a function of two variables. G of x and n. There are no h's in it. There's n's. And then we're dividing by h. So when you take the limit as h goes to 0, what ends up happening is the x to the n's cancel. And then when you divide by h, you can cancel the h with one of the h's up top. And now when you let h go to 0, what's going to happen is you're going to end up with n x to the n minus 1 plus, well, this whole thing is going to go to 0 because h goes to 0. Okay, and so you get this result from the binomial theorem. So this is another place where the binomial theorem is useful this time in calculus.